Hi friends, welcome back to another session. All these days what we have seen is the very old history, somewhere starting from 2000 years till World War One. Whatever encryption techniques were used, we have just checked them. Now from the World War Two, the whole scenario changed, and what we call is a modern cryptography. So let's see how the modern cryptography began and how it grew to the current state. So it all began in the Second World War. That was the turning point. That's between 1939 and 1945. So there was a machine called Enigma machine, designed by Germans. It was an electromechanical cipher device and used by Nazi Germany during World War II to encrypt military communications. So during the war, the communication is the most revered and highly respected one, because the whole result of the war depends only on these communications, and if we can trace out how the enemy is communicating among themselves, we can know their strategy and we can prepare our own counter strategy and all that. So that was a main issue during the war, and to ensure that the enemies don't understand our messages, we wanted to encrypt them before communicating, and the enemies always try to decipher the messages, and this uh, behind the scene war was going on. So it's something like a Cold War. Mainly it was between the US and the USSR. This Cold War was going on, and during this time the Germans were using the Enigma machine. So that's how the whole thing began. So this Enigma machine just looked like a typewriter, but only difference is whatever we type on the typewriter, it doesn't print the same character, but it prints something else, and that something else is decided by a complex set of internal wiring and other parts. It's a very highly complicated machine designed by the Germans, and this key, once a key A is pressed, the normal typewriter, when A is pressed, A gets printed on the paper, but in this Enigma machine, when A is pressed, something else gets printed, and that something else is decided by the internal wiring, and which is too complex, and cracking this was almost initially it was almost impossible, but it was broken by Alan Turing and the team. Alan Turing is the one who initiated the modern computer, and who gave the idea about the modern computer, and he is the also considered as a father of encryption. So he was the main person behind cracking how the Enigma machine works. So this team used the known plain text patterns and the mistakes done by the operators and the crypts, that is the guessable text, to reduce the search space. So the Nazis were sending the encrypted messages using the Enigma machine, and these encrypted messages, when they are found by the Britishers, they try to decode them, and Alan Turing and his team were all assigned this task to find a method to crack this cipher messages, and they try to use the known plain text patterns. So there was a text pattern and then some mistakes done by the operators and a guessable text to reduce this search space. So this breakthrough, that is breaking the encrypted code and getting the plain text out of the encrypted text, which was encrypted by the Enigma machine, laid the foundation for modern computational cryptography. So now onwards, computers enter into the cryptography world. Till now it was a human mind which was working, and now the computers start working for cryptography. Then 1949, Claude Shannon, who is considered to be father of modern cryptography, published the paper which is titled Communication Theory of Secrecy Systems. And with this paper, he proved that the one-time pad is almost unbreakable if it is used properly. Yeah, we had seen this one-time pad in our previous video, and there we realized that the USSR people, when they were using one-time pad, had committed some mistakes, like they had repeated the keys, and because of which they were cracked. But Shannon proved that the one-time pad is unbreakable if it is properly used. That means if the keys are not repeated and all that, and then introduced the idea of perfect secrecy. So the idea behind the Claude Shannon's work is he introduced that a bit as a basic unit of information. So in the digital world it is well known that bit is a binary digit. So the information content in any message is measured in terms of bits, and that was introduced by Shannon. And then the concepts of entropy, redundancy, and channel capacity were also introduced by Shannon. So the entropy is something to do with how much we can understand or how much we know, that is the information content. So any message will have an information content only if the information is new to us. If the message is already known to us, then we say there is no new information in that. So this is measured in terms of entropy, redundancy, and then we started talking about channel capacity. So the foundations of data compression and error correction were also introduced by Claude Shannon. So it gave a lot of initial steps for modern cryptography, and hence is known as a father of modern cryptography. Then comes in 1976, we started working with public key cryptography. So Whitefield Diffie and Martin Hellman published DH-key exchange. This allowed secure key sharing over public channels. So this is the first step toward asymmetric cryptography. That means there are two keys, one key for encryption and other key for decryption. For decrypting, the key is known to all. So if A wants to send a message to B, then A will have two keys, one public key and one private key. So the private key is used by A to encrypt the message, and the public key is already known to B. The public key of user A is already known to user B. and the user A encrypts the message using user A's private key, and the encrypted message is forwarded to user B. User B knows that this has come from user A, and he also knows that user A's public key, and using that public key of user A, the user B will decrypt the message. So that's a basic idea behind the asymmetric cryptography. Here the key to decode is known to everybody and is no more secret. So the whole secrecy is behind the key which is used for encryption, and that is only known to the one who is encrypting it. Therefore it is called a private key, and the other one is the public key. Then in 1977, RSA algorithm developed by Rivest, Shamir and Adleman. The RSA stand for these two people, were developed in 1977, and it was the first widely used public key encryption system. RSA is the first widely used encryption system using the public key, and this is based on the difficulty of factoring large prime numbers. So using prime numbers which are large in the size, so two such prime numbers are used, and a lot of circus is done with that, mathematical circus is done with that, and through that keys are created, and these keys will be difficult to crack, and hence without knowing the public key it is difficult to crack the encrypted message. So the encrypted message can be decrypted only by the users who have the public key of the sending end, and that's what a public key system is. Then in 70s, data encryption standard DES was defined, and this was published by NIST in 1977, and this is widely used symmetric key algorithm. That means the two ends will have the same key. The key used for encryption, the same key is used for decryption. So the sending and receiving ends sit together and decide the algorithm, what the algorithm they want to use, and the key. The algorithm is commonly well known to everyone. It is in the public domain, but what is secret here is the key, which only the sender and the receiver know. The sender encrypts the message using the key, and the same key is used by the receiver to decrypt it. Because both sides the same key is used, we call that algorithm a symmetric one. Eventually this became vulnerable because the key used in DES was of short length. Only 56-bit long key were used by the DES, and cracking 56-bit key using the modern computer is very easy, and hence that become a difficult one to continue using it, and therefore 2001 came up with advanced encryption standards AES, wherein this AES is going to replace the DES as a standard for symmetric encryption. AES is the new form of symmetric encryption which is going to replace it, and AES is efficient, secure, and still it is in use in the systems like SSL, TLS, VPNs, Wi-Fi encryptions and all that. Then from 1990s to 2000s, various cryptographic protocols were defined. That is SSL, TLS for securing websites. That is where the HTTPS comes into picture. Then PGP to secure the emails. Then came the blockchain era, where bitcoins started to use since 2009. So this blockchain is completely built on the cryptographic principles like digital signatures and hash functions and all that. So it's going to be more secure one compared to the earlier ones. And today we are into the quantum computing world. So we are working now with quantum cryptography. So some modern algorithms now may become uh, totally breakable through the quantum computers. Quantum computers are very high in computational capabilities, and the one which was once a dream to break any cryptographic system by normal computers is no more a dream if we start working with quantum computing, and that's what we are looking at. Once the quantum computer comes into reality, then all the modern algorithms just become useless, because quantum computing can break all the cryptographic algorithms in a matter of few seconds or so. So that's what we have in the future. So research is still ongoing into the quantum resistant algorithms. Yeah, we are looking at someday quantum computer may become reality. Therefore, today only we started working. If quantum computing is reality, then how to safeguard our messages? So quantum resistant algorithms research is going on them. So that's some history about what's going to happen, what happened post World War II till now, and what could happen in the future. So that's about what we have. Then getting into some taxonomy of the cryptography. So the cryptography can be viewed in different angles. So if you look at based on the key usage, then there are two types of cryptography. It's symmetric, asymmetric. Symmetric is one where encryption, decryption are done by the same key. So both the sender and the receiver should have the same key. Only then the decryption is possible. So the examples are AES and DES, and the other one is asymmetric encryption, wherein the sending is done using a private key and the reception uses a public key of the user who sent the message to decrypt it. So every user will have two keys, one private key, one public key. The public key of each user is known to all the users in the group who are allowed to use the messages. So if A and B want to be in communication, then A will know the public key of B and B will know public key of A. A has its own private key, B has its own private key. So if communication is between A and B, and if the message is being transferred from A to B, then at A, public key of A is used to encrypt, and at B the at A the private key of A is used to encrypt, and at B the public key of A is used to decrypt. Same way, if a communication is between B and A, that is B to A, then the encryption is done by the private key of B, and decryption is done at A using the public key of B. So decryption depends on who has sent it and the public key of the sender. If that is available with us, then we can decrypt it. So it is available only with the authorized people. Therefore, only authorized people can decrypt the messages. So that's a asymmetric version. Examples are RSA, ECC, and so on. Other way of looking at it, it's based on the function. It is encryption, hashing, authentication. So it just used for encrypting. It may be used, hashing function may be used for this cryptography, or it may be used for authentication like digital signatures and all that, or depends on the application. So it's data at rest, so we want to store the data and make sure that nobody views it, so we can have the cryptography for that. The data is being transferred from one point to another point, and on the transit we don't want the leakage of the data, then we encrypt at the transmitter side and we decrypt at the receiver side. Or want to check the identity before permitting someone to access our data, then we have that. So these are the three types of applications cryptography will have. Now looking at the taxonomy of crypto analysis, then crypto analysis, we can think in terms of information available. So the possibility that we have only ciphertext with us and we want to check, we want to break it. So that is what we call ciphertext only attack. We have plain text known with us. So we have plain text as well as ciphertext. So we just want to see how they are related, and with that, once we understand the relation between plain text and the ciphertext, then we can crack the future messages and all that. Or only a chosen plain text or chosen ciphertext attacks, then it may be looking the analysis is, we can think in terms of techniques. So it may be a brute force, that means try all possible combinations, and as we seen in the initial sessions, that brute force method, even if we are working at the fastest computers, the brute force method will take millions of years to solve the problems. Therefore it's not advisable. Then start using some logic in that, and that's where statistical analysis come into picture. Just find out the frequency of the characters used and then try to correlate with the ciphertext with the plain text and try to identify how the mapping between the plain text and the ciphertext might have done, and try to use that. And then mathematical attacks, differential or linear, maybe side channel attacks, and are different types of techniques used for analyzing the ciphertext. Depending on the target, it may be algorithm specific, or it may be protocol based, or it may be the implementation based. So depending on the target, that means you are targeting a particular algorithm, then how the analysis is to be done, we need to work on that. If it is a protocol based, then if we know what protocol is being used, then using that protocol and how to analyze or how to understand the protocol, or how the whole system is implemented and all that. So these are various possibilities we have in cryptanalysis. This all we are going to look in detail in our coming sessions of this. So that's it for this first module of BIS703. That's Information Network Security Module 1. So we look forward for the next module in the coming sessions. So keep watching. If you find the sessions of any use, please don't forget to like and share your views through the comments, and share the information with your friends. Please subscribe to the channel and hit the bell icon so that you get regular notifications as and when new videos are released. So that's it for now. Take care. Thank you.